Okay, continuing with complex numbers and still using De Morgan's theorem, we can use De Morgan's theorem to help us to summarise series involving trigonometry. So here we have two series. We've got series C, which is defined as cos theta plus a half cos 3 theta plus a quarter cos 5 theta, and so on. And a series S, which is very similar, except the coses have been replaced with sines. And in these questions, we're always dealing with the series amalgamation C plus IS. It's always that. Sometimes the question won't specifically use that, C plus IS, but in these questions it is always C plus IS. So we can use C plus IS to show that C is actually equal to this thing. So this is an infinite series, but it's actually just equal to that. And we're going to I'm going to introduce a technique on how to get to that in this video, and then there's also a very similar expression for S, which the question's asked us to do. So C plus IS, what that's going to do is it's going to be cos of theta plus I times sine of theta. Okay, so cos of theta plus I times sine of theta, plus a half cos of 3 theta, plus a half I sine of 3 theta, and so on. But using exponential form of this, we can state this first two terms as just being e to the I theta. The next two terms combine to give a half e to the 3i theta. The next two terms would combine to give a quarter. The quarter will come out. E to the 5i theta. So theta comes in. And then continuing that pattern, you would have an eighth e to the 7i theta would be the next term. And this is an infinite series. So we're summing an infinite series in this case. Sometimes it's finite. In this case, it's infinite. So you need to spot that it is geometric. And in these questions, if it's an infinite series, it will always be a geometric series. If it's finite, it might be geometric, or it might be a binomial one. So I've got a finite geometric one coming up, and then in another video, I'll have a look at some binomial ones. So the first term of this geometric series is e to the I theta. And then to get from one term to the next, we multiply by the common ratio, which in this case is a half e to the 2i theta. Don't forget that when you multiply by an exponent, you just add, when you multiply by an exponential, just add the exponents. So if I take this, multiply it by a half, and the half is there, and then the two exponentials come together to give e to the I theta plus 2i theta, which is e to the 3i theta. And the same thing occurs here. Half times a half is a quarter, so that half is coming into play again. 3i theta plus 2i theta is 5i theta, and it continues on in this manner. This is an infinite series, so n is infinite. And now with those three definitions that we've extracted from the infinite series, we can state C plus IS using the formula for summing an infinite geometric series. So it's S infinity is equal to A over 1 minus R. And that is going to be e to the I theta divided by 1 minus a half e to the 2i theta. Okay, so that's A over 1 minus R. At the moment, I've got a complex number on the bottom, so I want to make that real. So we're going to multiply the top and bottom by the complex conjugate of the bottom. So that's going to be e to the I theta multiplied by 1 minus a half e to the minus 2i theta. Don't forget, multiplying by the conjugate just means changing the sign of the coefficient of I. It's very tempting to change this sign here to a positive, but that wouldn't be the conjugate. You need to times the coefficient of I by -1 to get the conjugate. At the bottom, is going to be 1 minus a half e to the 2I theta multiplied by its conjugate, which is 1 minus a half e to the minus 2I theta. And because I'm multiplying a number by its conjugate, it'll be real. So the denominator will now be real. The top will be complex, but that's fine. E to the I theta. Okay, so times it by the number 1. And that's going to be minus a half e to the minus I theta. Again, don't forget, when you multiply the exponentials, you add the exponents. On the bottom, we're going to get a 1 plus a quarter. So that's 5 quarters. We're also going to get minus a half into e to the 2I theta plus e to the minus 2I theta. Let's multiply out the brackets on the bottom and the top. Let's multiply it by 4 top and bottom just to get rid of these fractions. And then I'm also going to note that this is actually just 2 cos of 2 theta. And how did I get to that? Well, that's a little aside. E to the 2I theta plus e to the minus 2I theta is equal to cos of 2 theta plus I times sine of 2 theta. Again, plus cos of 2 theta from that one. Okay, because the negative doesn't make a difference for the cos. And that's going to be minus I times sine of 2 theta, because the negative on the theta there actually changed the sign of the sine. The two imaginary parts cancel out, as we'd expect, because we expect the bottom to be real, and we're left with 2 cos 2 theta. So this c plus is is now just equal to 4e to the I theta minus 2e to the minus I theta, all divided by 5 minus the 2 there will cancel with a half, so the 4 actually affects the whole thing there, cos of 2 theta. Well, how does that help us find C and S? Because we've just still got the amalgamation. Well, C is the real part of this, and S is the imaginary part of this. Let's keep those on the screen. There we go. So C is the real part. And we know that this is equal to 4 into cos of theta plus I times sine of theta minus 2 cos of theta plus plus I times sine of theta. That 2 affects the whole thing there. And that is all divided by 5 minus 4 cos 2 theta. So it's the real part of that, so we can ignore the 2 signs at the top, and we're left with 4 cos theta minus 2 cos theta, which comes out to be 2 cos theta over 5 minus 4 cos 2 theta, okay, which is what the question required. Okay, there's what the question asked, and there's what we got. Similar situation for S. S is obviously the imaginary part of C plus IS. So that is going to be 4 sine theta there. And, oops, sorry, that's a minus, isn't it? Minus 2 times minus there gives a positive, so that's actually 6 sine of theta. Divided by that real denominator, 5 minus 4 cos 2 theta. And there's my expression for S. My second example is a finite geometric one. So very similar question, okay, by considering C plus IS show that this is the case. A little bit more elaborate because there are a finite number of terms, they have n kicking around as well. And again, it's C plus IS. So I'm going to go a bit quicker with this one. C plus IS is going to be 1. Okay, there's no other constant term. plus 3 e to the I theta plus 9 e to the 2I theta plus dot 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 plus 3 to the n e to the ni theta. So it's still a geometric series, it's just a finite one now. And the common ratio is 3e to the I theta, 3e to the I theta, and so on. So therefore A equals 1, R equals 3e to the I theta, and n, the number of terms, is actually equal to n plus 1, because this term here requires n to be 0. And we have the nth term over here. So actually there's n plus 1 terms in this series. So therefore C plus IS is equal to A into 1 minus R to the n over 1 minus R. Okay, that's the formula for geometric series for finite number of terms. Plug this in, we'll get 1 into 1 minus R to the n, so that's going to be 3 to the n plus 1, e n plus 1 I theta. Okay, so that's R to the n, bearing in mind n here is actually n plus 1. So 3 to the n plus 1, and that's to the n plus 1, divided by 1 minus R. Times that top and bottom by the complex conjugate. Okay, to make the bottom real. That's going to become 1 plus 3 to the n plus 2 e to the ni theta. So the minus 3 and the minus 3 to the n plus 1 is combined together to give positive 3 to the n plus 2. And the extra I theta from here, the 1 in the bracket, is cancelled because of the negative there. I'm going to get a minus 3 to the n plus 1 e to the n plus 1 I theta. That's 1 times that. And then finally I get the minus 3e to the minus I theta. That's all divided by the product of these two, which is going to be 1 plus 9, which is 10, minus 3 into e to the I theta plus e to the minus I theta. Simplify that a little bit. 3 to the n plus 2 e to the ni theta minus 3 to the n plus 1 e to the n plus 1 I theta minus 3e to the minus I theta, all divided by 10 minus 6 cos theta, again because that e to the I theta plus e to the minus I theta is 2 cos theta. C is the real part of this. So 1 is real. The real part of this is going to be cos n theta. So that's going to be plus 3 to the n plus 2 cos of n theta minus 3 to the n plus 1 cos of n plus 1 theta, and then minus 3 cos theta, and that is all divided by 10 minus 6 cos theta as required. And then the imaginary part, which is S. The 1 is real, so it just gets ignored. Get down. The 1 is real, so it just gets ignored. 3 to the n plus 2 sine of n theta minus 3 to the n plus 1 sine of n plus 1 theta. And then this is going to give me a minus sine theta here, but times that by minus 3 is plus 3 sine theta. And that's all divided by 10 minus 6 cos theta. And that is my answer for S. Thanks for watching.